Wonderful. Thanks for the invitation. It's a pleasure to be here. I know that I'm in a very delicate position because I'm standing between you and the buffet that comes after, so I'll try to keep things a bit distractful, let's say. When I chose the topic for today, because in the team we are doing a bunch of different things, I wanted to give you an overview, but at the same time being able to give you some details. So I decided to pick 3 works that I want to share and discuss with you. So the first hint when you want to guess what kind of works we are discussing is the name of the team. So it's Robot Learn. But then a few questions can appear, right? So which robots, which learning, and what for, right? So then maybe we can find some other hints on the title of the presentation. So it's multimodal perception, action, and evaluation of social intelligent robots. So that gives us a hint as for what kind of robots. Some people call it social intelligence, sociable, whatever. It's like robots that will be in the middle of, let's say, humans, and they have to deal with us, which is already painful for us. I cannot imagine what's for them. Anyway, so what for? Well, perceiving, acting, for sure, but at the end of the day, communicating, right? So we want the robots to be able to interact with people and to make sense of what people are saying and provide a decent answer in terms of speech, but maybe also in terms of actions, navigations, etc. And then what kind of learning? Well, that's not a very, how to put it, glamorous answer, but basically whatever works, and especially whatever generalizes, right? So the real world, as we have discussed today, it's much more complex than our data sets, and whatever works in our data sets then crashes directly when we try it on the real world, right? So to be more concrete, what I would like to present today is some work on unsupervised audiovisual speech enhancement. So that's on the perception side. Then a work that is currently under review on text condition safe social navigation on the action side. And then I'd say this is more like a collection of works that ended up with several waves of experiments in a hospital in Paris. And this is more on the evaluation of these beasts, let's say, in the real world. So let us start with the first part on unsupervised audiovisual speech enhancement using diffusion models. So this is John work with 3 colleagues from Inria and Nancy in the multi-speech team, Jean-Aude, Mustafa, and Romain. So for those who might not be very familiar with audio, I think that I am the only one that might say a few words about audio in this workshop. So speech enhancement, you can basically see the speech denoising. It's perhaps a little bit more general in the sense that the noise signal can be of very different types. But the idea here is that you have a noisy mixture that is here in the right in green, and you want to recover a clean version of that. So what actually the person said, not what the person said combined to a noise signal, right? So you want to get rid of the noise signal. Of course, this speech signal is a combination, let's say, of the way we move our lips and many other things in our body, and what we can register, like record with a microphone, right? So if we have the lips signal, it's perhaps a good idea to try to exploit it, especially if the audio signal alone is not reliable, all right? And then I mentioned unsupervised. So in speech enhancement, there are 2 main paradigms. The first one is what we call supervised speech enhancement, and it's basically a regression task where you learn a mapping between the noisy signal and the clean signal, right? So you have pairs of data. It's exactly the same sentence pronounced exactly by the same person in exactly the same way. And then you take this one, you add noise, and you have paired data, right? So this is very nice, but obviously it does not correspond at all to the reality. You will never find exactly the same sentence pronounced in exactly the same way that you will find it when you deploy your robot, right? So this is pretty obvious. So we try to step out from this paradigm by investigating unsupervised speech enhancement, which is you have a data set of clean speech of a bunch of sentences, right? And then you have your data set that has noise, but you don't have per data the same sentences with and without noise, all right? So this, of course, corresponds a bit more to what we want to do, because at the end the robot will not encounter this, but it poses other problems. As we will see, it's a bit more slow at inference. But once again, it's much more robust to out of distribution, as we will see later in the results. So, what is our choice here? We will learn a model for the clean speech data, right? So here there is no noise. At training time, we have no noise, we have only clean speech data. Then once we have this is frozen, and we go to the second step, which is test time. And then at test time, we have this model, the first part that is frozen, and we have a noise model, and we only observed the noisy speech, which is this one on the right, okay? And now we have two tasks. We have to learn the parameters of the noise and estimate the clean speech signal, all right? Now, I don't know if this is 0 shot, 1 shot, or whatever, but the thing is that this test time works with one sentence, right? So I'm learning the parameters of the noise with only one sentence, right? So this is very low data regime, I would say, all right? So because we have these two differences in the sense that the training, sorry, let me show. So the training, I can have as many data as one, but the test is only one sentence. The models for the speech and the noise are very different. Like in this model for the speech, so we will be using a diffusion model, but it can be a very deep and powerful model because I have a lot of data and I have a lot of time to train it. When I go to the noise model, then I cannot have a very deep model. I only have one sentence, so I will have a very shallow model, and it has also to be as quick as possible because I'm at test time and I don't have a lot of time to make the user wait, all right? So, I guess you all know diffusion models, just quick recall maybe. We have this data on the left, and then the forward process adds noise here, and then the reverse process, we know it exists and it's unique, and it has this form. Problem, this is impossible to compute in closed form, so what do? We learn a score function that approximates this stuff, right? Which means that once we have learned this, in order to recover a clean speech sample, I have to integrate this stochastic differential equation backward in time, all right? This is a lot of steps, all right, going back. So this is computationally a little bit expensive, and this will be important in a few slides. So let us assume that we have our clean speech model, and then the problem that we have, as I said, at test time, once theta is done, it's worrying about my noise, right? So to do that, I can pose this equation, which is a maximum likelihood equation. And while this here is my noise model and it's well under control, this is the posterior distribution of the clean speech given the noisy speech. And this is very challenging to estimate. And we will be actually working with an EM algorithm that might look like ancient magic for some of you here, for the most young people. So we will be celebrating, if I would say, the 50 years of the EM algorithm in a couple of years from now. So this is a bit old, but still works very well. And it's especially good when you have probabilistic learning problems with latent variables, which is the case here because our clean speech, right, this S, is a latent variable now. We don't observe it. Now, the key idea here is to use a conditional diffusion process instead of an unconditional diffusion process, all right? So I repeat again, this X here is my noisy signal, and then I would like to consider a conditional diffusion process instead of the unconditional one, right? But now you might say, this is very close to all these works that use, let's say, for instance, text-based image generation, right? It's still a conditional diffusion process. So what's new here? What's going on? What are you telling all these? Well, this is just something that has been done like 3 or 4 years ago, right? The main difference is that when you have text-based text condition image generation, you learn the diffusion model with the condition. On our case, we have learned the unconditional diffusion model, and now we want to consider the conditional one, all right? And as I told you before, we only have one sentence for that. So it's impossible that I use the standard way of training diffusion models. So what are we going to do? Instead of considering the unconditional distribution, right? So this is the regular backward stochastic differential equation. I'm going to use the conditional one here, right? So that's what I would like. Knowing that, I insist, this model has not been trained with a conditional distribution. So I have to do something else here. I have to be a little bit smart. So that's what we try to be. And we actually realize that this log here can actually decompose in the sum of two things. The one on the right is exactly what I trained for. So this can be approximated by the score model of the unconditional diffusion process. And this one, believe me or not, after a few mathematical derivations, you can express it as some sort of score model that takes into account the noisy speech here. So that's good, because now this means that I can put this part, these two terms here, back into my SDE, and then I can actually sample backwards from this stochastic differential equation and obtain a clean speech signal, right, that corresponds to the current noise model given the noisy speech. So that's very nice, and that's actually the E step of my EM algorithm, all right? And then whenever I have one sample of this clean speech, I can go back here, I have my sample here, and I can update the parameters of the noise, all right? So that's very nice, but it's not super efficient. Why not? Because look at what happens here. You know, EM is alternating between these two things, right? This is very efficient, but this is sampling back, right, all the way from the noise to the clean speech signal, okay? So this means that at every E step of my EM algorithm, I have to do one backwards integration of my SDE, right? Not very nice. The other problem is that so far we only used audio, and I promised audiovisual speech enhancement. So right now you have the right to be angry at me, but I will try to solve this issue right now. So for the audio part, it's going to be very easy, or at least very intuitive. Now my score network is going to have these visual features that I input through cross-attention, and basically now the score is a score that depends, of course, on the current estimate of the signal and on the visual input, all right? That's very standard. And now basically I will be learning a score, as I said, that depends on S, but also on V, right? And these will be replaced into this backward SDE. And now for the second part, the idea is to have only one backward integration. And how do we do that? It's instead of going back to the clean speech and update the noise parameters, every time we do one step of the SDE, we update the noise parameters. One step here, one update. One step, one update. So that's not an EM anymore. It's kind of a hybrid thing. But this means that we only do one backward integration of the stochastic differential equation. And why this works, actually, the reason is that at the beginning, when you have like a very pure noise signal, the exact estimate of the noise parameters is not very important. It's not very crucial, right? Because anyway, this is pure noise, right? So we don't care. And then little by little, when you get closer to the clean speech signal, of course, having a good estimate of the parameter matters, all right? That's good. I wanted to show some results, of course. Here you have 3 plots. Each plot is a different metric. All the 3 metrics is the higher the better. And for each of the plots, you have 2 sets of bars. The set in the left, it's written matched because the train and test follow the same distribution. Okay? And the one on the right, the train and test, follow different distributions, so it's unmatched. All right? And we are comparing here the input, which is in gray, a supervised model that you can see here in red, and then 4 unsupervised models. Let's say the plus is for the acceleration, so it's when we have only one backwards integration, and then AV, surprise, is for audiovisual, right? So what we can observe here, we can observe a few things. Whenever you take a look, whenever you compare to match and unmatch, you can see that the red bar is basically going down severely, right? This is the supervised model. The supervised model cannot handle, it's very difficult for that model to handle a change of distribution, right? Of course, the unsupervised models are not perfect. They are not completely robust because they have been learned on the clean data, on the clean speech data, but they are much more robust to changing both the speech distribution and the noise distribution. And then another thing that I think it's interesting is that systematically, when you compare the light yellow and the dark yellow and the light blue and the dark blue, which is basically adding the visual information, you can see that there is a systematic increase in the performance, whatever the metric, whatever the conditions. Another thing that it is also very intuitive is when you compare the 2 lights and the 2 darks, which is basically having this simplification of the algorithm that is only one backward sampling. Of course, the performance decreases a bit, right? Because it's a much faster algorithm, but it's less, I only estimate, I only do one backward, and at the middle, the noise parameters are not very well, okay? So of course, it has a negative impact, but it's, let's say, mild compared to what happens to the supervised model. All right, so that goes for the first topic I wanted to discuss. And then we can open, let's say, the floor to the new topic, which is text condition safe social navigation. And that's under review, and it's joint work with Jordan, which is in the room somewhere, and Pierre Ruiz here at Inria. The idea here is to be able to give language instruction to the robot, and that then the robot navigates and complies both with the language instruction, obviously, and with, let's say, some standard safety constraints, like not colliding with objects, not getting too close to people, if possible, and so on, right? And then the idea here, as I said, is that the speaker that is in yellow will say, for instance, come close to the table, and then the robot has to go to the table without colliding with all the other people that you can see in the room, that of course moving at their own pace and will. So here, to address this problem, we introduce Listen, which is a very nice name. If you are giving instructions to the robot, it's supposed to listen, which is generating language-grounded safe social navigation in crowded environments. And it has 3 steps. One step, the first question that we needed to solve is how do we generate data so that we can train a model, then train that model, and what kind of model, how do we train it, and then the evaluation when the model is, let's say, running in an autoregressive way at test time. So for the data generation, I'm going to detail these 3 steps, of course. So for the data generation, we had a bunch of commands, let's say, that can be either related to a human or to an object, or related to the robot, okay? Here I show you left of whatever, right of whatever, but we have actually generated a bunch of sentences that relate to that particular command, okay? So there is a variety of ways you can express that. We try to take this into account. And then, how are we going to actually generate data? We use this spatiotemporal RRT, so this rapidly exporting random tree, in which we consider, of course, our 2D environment, x, y, and then time. So here, the vertical axis is time. That's why, so for instance, this wonderful green cylinder is a plant that doesn't move, it's not supposed to move. This is a table, stays in time, and then all these cylinders that you see in different colors that actually move are supposed to be people, right? So once you have this, then the robot starts whatever, the command is go to the table, and then you're going to be sampling points, and then finding trajectories that do not collide with people and with objects, okay? And then reach the goal, if possible, in a way that you are compliant with the instruction that was given to the robot and also compliant with safety considerations. And like this, you can generate, of course, many different trajectories that satisfy these two constraints. And you can build a data set, and then you can pick up whatever model you prefer. In our case, was something that was very close to GPT-2, that had multimodal input, and that was supposed to estimate the displacement of the robot, the trajectory of the robot in the future, given what? Given, of course, the position of the robot and the orientation of the robot and the rotation of the emitter, given also the observation of the robot. In this case was some sort of augmented LiDAR with semantic classes and the speed of the point in that direction. And also we need to take into account the language instruction, and this was simply a mini-BERT or a BERT mini encoding of that instruction. So all this is given as input to this transformer that outputs both the displacement x, y, and time of the robot, and the flag that is saying whether or not it's the end of the sequence, basically whether or not you are done with the trajectory. In terms of losses, you are tempted to be using only the standard supervised loss for transformers, but this is far not enough. It's good, it's very good to use the other things that we said to comply with the language instruction. In that case would be the distance to the goal, and to comply with safety, right? So basically to have, sorry, if I point to my screen you don't see, to have collision penalties, all right? So the exact formula you can find on the paper, but you get the idea. And then once you have done that at training time, at inference time, the model, of course, runs in an auto-regressive manner. Okay, so every time step, you predict a new thing, you get new observations, and so on. So we have two, I want to present two sets of results. The first one is this table that shows how many times the robot is compliant with the instruction, because if we don't even have this, well, who cares, right? We will worry about safety later, but at least does it do what we want? It's mostly yes, not all the time. Some tasks, some instructions are more difficult to handle than others. I guess that the plant here, one of the issues is the size. It's very small, so it's much more difficult to take into account. Yes, and you see also in some cases, so basically the difference between failure and collision, well, collision is collision, and then failure is basically you don't reach, within the timeout, you don't reach the goal, but you don't collide either, all right? And then we have also a small table here that shows a few metrics compared to, let's say, one standard baseline, which is ORCA, and then two kind of recent things that we could train to compare our work with. And you have here several metrics. So the first column is which is the percentage of times, well, the proportion, not the percentage, that we get into the personal space of someone. Okay, so of course we want this to be as small as possible. The second one is a collision rate, either with a person or with an object or with a wall. Then the time to reach the goal, the timeouts, the percentage of timeout, again, proportion, and then the path length. So what we can say is that, okay, we are either comparable or better than what's out there or what we could find out there. But we can still see that, I mean, the personal personal space is okay, like 0.2% of times we get into the personal space. Maybe that's not that bad, but the collision, this is not good. I mean, 1%, 2% collision is something you really have to work with, especially when you want to deploy this in the real world, right? It cannot be that 1% of trajectories collide. That's not satisfactory. So we still have some work, and all this is in simulation, right? So I am very sure that whenever I put this on a robot, these numbers will basically explode, and we will have to work much more. Yes, I wanted to show a video. So this is video of the results. We have a few examples here. You can see, so basically it's either, that was very fast. Okay, so get behind me, stop near the plant. So it has to go through the plant. You can see that it avoids people fairly well. Sometimes it gets scared, so then it goes very slow, right? It gets kind of blocked. So this was not even a timeout, but still one of the ones that took a lot of time. And then stand behind me when there is people like between the robot and the behind me. It gets also very complicated, right? But yeah, you can see that it is actually complying with the instruction and still being reasonably safe. That's good. So I wanted to go perhaps to the last point, which is going to be, you see we have seen two fairly technical contributions. Now I'm going to describe more a high-level thing. It's a result of a whole project. And the reason I chose that is because maybe it steps a little bit out of my comfort zone. That's a bit dangerous. But also I think it's important to realize that when we talk about AI and robotics and we want to have a real evaluation of this, there is no other way than stepping outside the lab. Okay? So I wanted to bring this argument to the table. So here I couldn't put the list of people that is involved within that because it would be a very, very long list. It's more than 40 people, even more than 50 probably. But there is at least Radu, Nicola, and Soraya that were here before, that were involved in that. And these are basically the results of 4.5 years of research that was done in the framework of an EU project. All right. Good. So the project was, let's try to make these robots be able to work in these scenarios here, right? Be able to move, see, hear, and communicate in such scenarios where you have a lot of people, you might have noise, you have like lots of dynamics, multi-part interaction, whatever you want, okay? So we had to put together 8 different partners that had very different skills because it was a very tough thing to do. So we had all this objective of new machine learning methods that then we can be implemented in a robot, and most importantly, that can be evaluated, right? And I will spend some time explaining how this happened because I think it's very interesting. So the way we worked is we considered a bunch of use cases. They were motivated by discussions with one of the partners, that was a hospital in Paris. This gave us requirements for our models that we implemented in software modules, and then within a robotic architecture. Then we sent this to the hospital, they came with feedback, and then we had to change that and change that and change that, and then feedback again, and blah, 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 blah. Why I'm saying this? Because I think that most of the times, most of the research that I'm doing, it's basically these two things, right? And then, yeah, well, the robot, whatever, and of course the user, it's not even in the equation, right? And I think it's important sometimes, someone was asking about use cases before, and we were very lucky to have this from the hospital saying that's what we want. Of course, some things were impossible, but I think at least we were doing things because someone was needing that, right? So that was a very nice feeling, even if it took a few iterations. So that's how we thought the architecture, the software architecture would look like. Right? That was our mind set up before the project started. And this is what happened during the project, all right? So, of course, I'm not going to detail any of that, but this is also to say that whenever we say this is going to work on a robot, well, take it easy, huh? Because there are many blocks in here that you might not have control over, and it's going to be very difficult if you don't know them very well, if you don't have proper engineering people to make your wonderful transformer work with the data that comes from the robot. So once we have done that, we can think about the experimental protocol that happened in 2 steps. The first step is getting people that actually want to come and test your robot. Okay. This is not a very easy thing, right? In addition, this was a gerontological hospital, so the average age, I think it was something around 78 or 81. So those people don't really like technology sometimes. Anyway, so you have to call them, you have to explain them the project, you have to convince them to come and test your robot. And then on the D-Day, well, you have to talk again about the project, about the robot. You can make them interact with ARI, and then you have some questionnaires here that then you can extract results from, okay? So we had 2 main questionnaires, one that was assessing the acceptability and one that was assessing the usability, all right? So these questionnaires, like for the acceptability, there has questions like how easy did you find the robot to use, how understandable were the robot's requests and suggestions, and so on. And then in terms of usability, it's like, would you like to use this robot as often as possible? So I think I think I will need help to interact with this robot, and so on, all right? So these 2 questionnaires have these cutoff scores. These are a little bit, how to say, not very adequate because they are cutoff values for end products. So this is basically when you have the product completed out there, while we were not even having a prototype. But anyway, that's how the scales work. And in the, yes. So these are pictures of actual patients and personnel, medical personnel interacting with the robot. It was the ARI robot that you can see. It's very cute, but it's actually pretty tall. It's like 1.6 meters. So for some people, that was a little bit scary. Okay. And then once you have done all this, something very fancy to consider as well is to get the ethical approval, all right? And you have to do this depending on where you want to do things. You have to go through your, let's say, institution's ethical committee, but here in France, there is a national-wide committee, which is called the People's Protection Committee, that you might have to reach, and they might constrain the way they consider necessary your experiments. And in our case, at the beginning, we proposed to have, let's say, robot days, where only people that wanted to interact with the robot would go to the waiting room, and then not robot days for the other people. But here in France, we have something that is called universal access to healthcare, and constraining the people that didn't want to have to, nothing to do with robot, not to be able to go to the hospital was not acceptable. So in that case, what do? Well, we put the robot in another room, and then only the people that want to interact with the robot go to that room and then can have the interaction. And why I'm telling this story is because the results that I'm going to show right now are obviously biased. Why biased? Because if only people that want to interact with the robot go there, well, people will be happy, right? If you have to face someone that doesn't want to interact with the robot, maybe your acceptability and usability scores will be very different, okay? So that is field issues, let's say. So basically, we had two different waves, one with 20 people, one with 49 people, and we measured acceptability and usability, are normalized the scores up to 10, so that it's a bit more readable. So, because it is biased, the absolute values are not really important, but what we can see is that from the first to the second wave, both scores, this is mixed up actually, both scores improved, right? And the main reason for that is actually double, is that we have improved the ASR from the first to the second round, and we actually included a large language model to handle the dialogue, all right? So that means that people could speak, so the robot would understand many more things. And then, of course, the consequence of that is that people find it a bit more acceptable and much more useful or usable, all right? Okay, good. So I am going here to the conclusion, where I would say that generalizing things to multimodality, it's very interesting, but it is also very challenging, as we have seen for the speech enhancement. Implementing methods and models on a robot requires a lot of effort and engineering effort and discussions with between engineers and researchers. But when you want to go to real evaluation, you have to include people from the real world. And my advice is you also include people from human sciences, because they know what things mean for users. We don't, okay? They do. So if we want to go look, let's say, a bit beyond all that, of course, one thing that we are looking into is how to link all these multimodal LLMs or models that can absorb multimodal data in a robotic platform. What happens when you have this distribution shift from a steady camera to the camera that is on a robot, or from the microphones that are in a robot, and at the same way, how to generate multimodal stuff. So Adrian mentioned that before as well. Having a large-scale evaluation, we always talk about large scale, but in this case, it's even more difficult, because this means having hundreds of users coming to test your system. And then basically also another step forward is to go to real autonomy, perhaps through communication. And by that I mean that even we saw before in the video from NAVER labs, these people trying to block the robot, right? Well, then at some point the robot needs to understand that and say, guys, that cannot go through. Can you please let me, right? I mean, that you need this communication to kind of, that's what we would do, right? And certainly there might be many other topics. So I just want to, with some small advertisement, we are organizing this winter school in a few months. I allowed to put this because we have you have one of the suspects coming here that you might know. So if you don't know what to do that week, or if you know but you believe this is better, please go there, check it up, and register for the winter school. Thanks.